Sir, shall we start the session? Are you ready, sir?
Yeah, please, I am ready.
Yeah. Good morning, dear contestants. Very welcome to you. Today we are about to start the session. The session will be handling by Dr. P.V. Unnikrishnan. I have to give you a brief bio about sir. Dr. P.V. Unnikrishnan has a rare blend of academic, research, government, professional, and consulting experience over 36 plus years. Trained in EC engineering and e-govern both in India and abroad. He has worked 36 years in the government in roles like COO, CEO. He has rich experience in technology development and development sector. He had 5 years sabbatical at KSSP Research Center, where he was exposed to innovation, emerging technologies, livelihoods, renewable energy, small hydro development, and watershed management. He was involved in Kalyashiri integrated planning exercise evolving as people's planning program solutioning capability building for equitable growth. He's he spearheaded for 15 years planning implementation of mission critical projects in decentralized planning, administrative reforms, BPR, service delivery, e-governments, and KM energy. He consolidated domain knowledge in 7 volume system manual of LSG systems and developed 12 software apps covering resource utilization and customer management in the first ever e-government for LSGI in work, including the just a sec. During 2006-2011, he was non-minister member of SPB Kerala, in which with a rich experience in infrastructure, energy, governance, tourism. He had worked 4 years as STEP trainer for NISG. We are very proud to have you here, sir. Before that, I also invite Dr. Ahmed Pinsa, HOD of Mechanical Engineering, to give a brief about our speaker, Dr. P.V. Unnikrishnan, sir. Ma'am, please.
Thank you, Vishal. Thank you. A very warm good morning to one and all. We are going to begin the third day of our faculty development program, Entrepreneurship and Essential Skills for Innovation. On behalf of the Department of Mechanical Engineering and MES Management, I take the privilege to welcome Dr. Unnikrishnan sir, Member Secretary of Kerala Development and Innovation Strategy Council, KDISC, to this session. As a member of State Planning Board, the initiatives that he has taken for strengthening our local self-government institutions and in implementation of People's Planning Program is very much known to all of us. Being a social engineer, come academician who lead innovation programs to the state, I am proud to say that he is the apt person to chair today's session. Hearty welcome, sir. Thank you. Thank you all.
Thank you. Thank you, madam, for the nice words that you talked, and thank you, Vishal. I'm extremely happy that the MES College has taken this initiative to launch this entrepreneurship program and also organize a session covering Industry 4.0. I will straight away go to my presentation. I hope the slide is visible.
Yes, sir, absolutely.
Yes, sir.
Let me just see whether the slide changing is also working. Yeah.
Yeah.
Yeah. So what you are seeing now is the cover page of a very important publication, The Fourth Industrial Revolution by Klaus Schwab. He was the founder, executive economic page. As you could see, it talks about a variety of things. The rightmost you see the disruption of jobs and skills, innovation and productivity, inequality, as a sort of important issues arising out of fourth industrial revolution. It is expected that as a part of the fourth industrial revolution, there is going to be huge change in the workplace which would result in displacement of 25% of all employed throughout the world. At the same time, it also will enhance productivity drastically and brings in opportunities for improving the manufacturing and service process continuously with the infusion of innovation. It might foster inequality widely because, as you are all aware, men dominate computer skills and engineering. And so the inequality that is likely to come up as a part of fourth industrial revolution is going to be profound. So these are the issues that we would discuss. Before that, let me just go to basics and talk about what the industrial revolution is about. This slide, as you see, on the left-hand side, we see the 18th century when we had the first industrial revolution. That is the period when the humans started moving from agriculture, settled life. If you look at history, we all know that settled life started moving from the hunter-gatherer society into the river valley civilization, where crops were planted. Human and animate energy was used for production, transportation, and communication. Settled life, urbanization, improved food production, increased population growth, and rise of cities was the major feature of this period. It was following this. It was following this that we had the first industrial revolution, wherein we had mechanical production facilities using flowing water and steam power. The first mechanical loom was established during this period. The second industrial revolution, the figure that you see is basically the production lines in the Cincinnati slaughterhouse in Chicago. Ford, who developed the model for assembly line, has indicated that it is from the slaughterhouses where people were standing in a row and animals were vertically aligned and they would cut one part of the body after the other in tandem. That was the first assembly line which was established in the Cincinnati slaughterhouse. It was this model which Ford used for better division of labor and mass production using electrical energy in his workflow, in his assembly line system. The second industrial revolution is thus related to use of electricity. It was during this period that flow production and assembly line opened up opportunities for replacement of labor by technology. Taylorism, time and motion studies, etc. are important features of this period. Steel production, electric motor, incandescent engines, development of turbines, plastics and rubber, these all transformed manufacturing. Telephone was developed during this time thanks to Marconi. Vacuum tubes and radio improved communication. Fertilizers and pesticides helped enhance agriculture productions. Breakthrough in pharmaceutics, disinfectants and antiseptics improved healthcare. Dynamite made possible construction of tunnels, roads, oil wells, and quarries. This was the second industrial revolution in the 19th century till the beginning of the 20th century. We had subsequently followed by the third industrial revolution. The important feature of the third industrial revolution, or IT revolution as we say, is usually people say that it is the emergence of computers. But actually, the most important hallmark of the third industrial revolution or the IT industrial revolution is the manufacturing automation via the electronic and IT systems. The first programmable logic controllers, PLCs, which are being widely used in process control systems, originated at this period. Then, of course, there was the computer revolution, which was followed by the internet and the World Wide Web. We will go into a little bit detail of what the third industrial revolution which we are talking about. Very few people know that even now, 100% of the credit card transactions and 90% of the Fortune 500 companies depend on the IBM mainframe and not our PC. IBM mainframe was a technology which was kick-started by IBM as early as 1960. It was in 1980 that the personal computing era started off. And the office systems that we use, the spreadsheets, the word process, and the productivity tools came to origin at that point of time. When I was starting my e-governance career, at that point of time, the technology was called client-server technology, where you had powerful server computers linked to desktops and PCs as clients. This was what was done during the 80s. During the 90s, there was a need to, a variety of local area networks and wide area networks were established, and it was necessary to link them together into a single infrastructure. And it was at this time that the World Wide Web came to existence. As I had indicated, the programmable logic controllers is the most important feature of the third industrial revolution because it made process automation possible. Process automation was born in the automotive industry. Subsequently, it has spread to industrial automation in glass industry, steel and cement industries. Examples of locations where PLCs are used are robotic manufacturing and control, car park control, train control station, food processing, material handling, machine tools, conveyor system, etc. But it was not the programmable logic controllers which was the central theme of transformation of the IT revolution. The central theme of transformation of the IT revolution was what is called the digital revolution. The digital revolution, as you are all aware, what is digital, what is analog is what exists, analogous to what exists in the nature. It is continuous variation. And on the other hand, we have digital where we have ones and zeros. It is on and off switch based, which is basically a analog to digital conversion based system, if we can say, comparing with the natural system. The A to D conversion systems have become more robust, and also the digital compression technologies have also given opportunity to what is called the digital revolution. But the most important feature which led to digital revolution is what we call the micro miniaturization technology, which is made possible by solid state physics and breakthroughs in very large scale integrated technologies. In order to quickly explain what the micro miniaturization is about, I would make a comparison between the grandmother of computers called the ENIAC and our iPhone. The ENIAC, which is shown on the top, had got 17,468 vacuum tubes. It occupied a space of 1,800 square feet. It had 25 tons in weight. It was capable of executing 5,000 instructions per second. It had a power of 175 kilowatt. When the ENIAC was switched on, lights dimmed in Philadelphia. And when ENIAC was shut down, it had to be water cooled for hours. We know the comparable product, the iPhone, is very familiar to us. It has 4.3 billion transistors. It has a space of 180 square centimeter. It weighs 170 grams. It can execute 25 billion instructions per second. And it has a power of 800 milliwatt. It assumes a power of 80 milliwatt. And what has made this possible is what we call as the Moore's law, which essentially means that the density of transistors in an integrated circuit, because of growth in semiconductor technologies, the density of the transistors had been increasing at a pace that the CPU capabilities the CPU capabilities had been doubling. The speed of the CPU had been doubling every second year. And this was called the Moore's Law, which was by Gordon Moore, who was the head of the R&D at the Fairchild. And he co-founded the Intel in 1965. And the Moore's Law has remained accurate for several decades. But nowadays, we find that the Moore's Law, because the size of the integrated circuits becoming very close to the atomic size, there are serious challenges that are coming up with further growth of micro-miniaturization. And as a result, the Moore's Law has started fading out. Another feature that led to the revolution, the digital revolution, is the digitization, which I told you. Digitization, as I told you, is conversion from analog to digital. The photographs which are shown below, they are basically achieved through digitization. On the left side is an analog picture, on the right side is a digital picture. It is hardly difficult to make out any difference between the quality of the picture using our eye. In order to explain what digitization is, I will make a very small comparison of international telephone prices for a 3-minute call from New York City to London. In 1930s, when the first call was made with the Marconi's technology, the charge of a call to be made, the expense for a call was $75. It involved 200 hours of manual work. In 1999, when a corresponding call is made, the cost of the call is $0.3 or 30 cents, and the hours of work is 0.02 hours. This is the transformation which has been made possible through digitization in the area of communication. Another very important breakthrough in the area of digital revolution which has made possible was the convergence between the computer, the communication, and the media. There is very hardly any difference between the different forms of the media. Nowadays, newspapers have online channels which provide video. The TV provides interactive chats, and radios have webcam. So the traditional boundaries of the different medias are no longer existing. Magazines, radio programs, TV shows, and movies are available on the internet through laptops, tablets, and smartphones. We have voice over internet protocol, and you can make calls, you can use video phones, you can use voice on demand service, and also digital video on handheld devices. So we see that there are a number of convergent devices, be it a digital camera, an MP3 player, all of them are having a variety of convergence. So there is convergence at the device level, there is convergence at the type of media level which handles content communication and computing. This convergence has made irrelevant the barriers between different forms of media, and this is one of the important features of the digital revolution. Another feature of the digital revolution is that we have a variety of privacy challenges. A lot of applications like the Facebook and various other applications are picking up quite a lot of personal data, especially on the cyber world. And then the Cambridge Analytica scandals have resulted in situations where personal data has been shared by these entities without the permission of the client. WikiLeaks has exposed several cases of infringement of privacy by the state. Similarly, the Government of India, many initiatives of the Government of India have been questioned by the judiciary as well as civil rights activists in terms of individual privacy. So this is a very active issue which is being discussed world over. Now let us come to the fourth industrial revolution. The fourth industrial revolution, it is basically It is an area, if the third industrial revolution was relating to hardware automation, the fourth industrial revolution related to software automation. The single feature of the fourth industrial revolution is the emergence of cyber physical systems. The third industrial revolution was primarily relating to the IT revolution, relating to the cyber world. It created a new opportunity around the cyber world. Whereas the fourth industrial revolution arised out of the fusion of the digital world, the biological world, and the physical world. This is the most important feature of the industrial revolution. It is no longer limited to the IT revolution, but on the other hand, it relates to life sciences, it relates to material sciences, it relates to nanotechnology and the micro miniaturization, which is furthered by the nanotechnologies of the world. We will quickly look at what are the aspects of the fourth industrial revolution in a few slides in my presentation to come. Subsequently, I will look at how the entrepreneurship world over systems are getting transformed in the context of the emergence of the industrial revolution, and thereafter my presentation will close. Now, coming to gene sequencing, let us look at what gene sequencing is about. I have only learned life sciences or biological sciences up to the matriculation. But I have compiled some material for the sake of this presentation. As you are all aware, the major breakthrough that we had in life sciences during the last several decades is the Human Genome Project in 1990-2003. The most important aspect of the Human Genome Project is shown on the right side, where the genome sequencing costs. The curve, the white curve that we have shown, the white straight line that we have shown is a Moore's law curve we have been talking about. So there is a particular slope at which the speed of the IC, the integrated circuit, had been increasing. That is an improvement in semiconductor technology. The green graph, the green curve, is the cost per genome. As you can see, the cost per genome had been decreasing at a rate which is much faster than what the Moore's law costs. We have seen the cost of telephone call coming down. So much faster than the progress in digital world, there had been transformation of the cost per genome. It was 2.7 billion. 2.7 billion genomes sequenced in a few hours for a few $1,000s. So from several $billion, it has come down to a few $1,000s in after the whole genome revolution. It is not only the analytical capability of the huge computers which analyze the characteristics of the genome, which is the important advance in life science. Synthetic biology is one area which has made huge breakthroughs. What I have shown in the picture is a skin printer, which is not a science fiction, which is now available. The technology of the screen printer is basically shown at the left, where we have bio-ink spheroids, which are emulsion materials printed onto a bio-paper gel. And additional layers can be printed on the layer. And these bio-ink spheroids can join together and the bio-paper can dissolve. And you have final living tissues created. All these are possible now through what we call the skin printer. This has given huge opportunities in terms of synthetic biology. This means that if you find that, if you have a feeling that your nose is not appropriately fitting you. It is possible for you to burn away the nose by using a laser, and you can create the 3D model of the nose you want and then replace it, which can be reprinted by synthetic biology. It is possible now to transplant organs by using synthetic biology. What is the importance of transplanting organs? Let us see this curve of transplants. As you could see, the yellow curve at the bottom is basically indicating the demand of, is basically the number of transplants which are happening. The blue curve is the number of transplants which are happening. The yellow curve is basically the number of donors which are available. And the red curve is the waiting list for organ transplant. As you could see, the organ transplant requirement is continuously increasing. And we are not in a position through the donor system to address this. So what is the way out? The way out is called xenoplantation. The xenotransplantation. Let us see what xenotransplantation is. Xenotransplantation means it is transplantation of a body part from an animal. And the animal which is closest to the human body in terms of characteristics is the pig. And what has now been achieved is, it is possible for us to get a pig kidney and replace the kidney in the human body. But the human body has a system which rejects the recipient kidney, indicating that the kidney is from an alien species. But now we have found out a mechanism to overcome this. If we are in a position to administer pig bone marrow cells to the recipient prior to the organ transplantation, the donor immune cells will not attack the transplanted organ, because the body will now, because of the transplanted pig bone marrow, think that the kidney is that of its own species, and therefore it will not reject it. So through a process of conditioning, preconditioning of the recipient through the donor bone marrow, it is possible to have immunosuppression and xenotransplantation. This is fast becoming a reality, drastically transforming the situation in terms of organ transplantation. Another interesting area is disease treatment. We are all aware about this whole technology called CRISPR editing. CRISPR editing is a technique for which the 2020 Nobel Prize in Chemistry was given to Emmanuelle Charpentier and Jennifer Doudna for this achievement of CRISPR technology, for CRISPR-Cas9 technology for editing genes. In the body, there is a normal mechanism by which a tumor cell is rejected. Now, in the CRISPR editing, what is being done is the normal rejection, which is done by the T cell of the tumor cell. What happens is that the T cell, it is through the T cell response that we recognize the tumor cell. But what happens is that there is an equilibrium which is established after some time, whereby the tumor cell rejection by the T cell is inhibited. So what we are doing is, we are removing that inhibition, so that through the CRISPR editing, just like we edit a Word document, it is possible to do the gene editing. And because of this, the rejection of tumor cells can be further activated, making possible the treatment of cancer through gene editing a reality. There are also neurotechnologies, novel neurotechnologies like transcranial brain stimulation, the TBS technology, deep brain stimulation. These are all becoming possible with major changes in the brain-computer interfaces and also various invasive procedures which are now possible. Neural stem therapies have also come up, which has drastically transformed the possibility of intervening with the human brain systems as well. So the breakthroughs in life sciences have become very drastic. This raises a variety of issues, ethical issues. This raises a variety of ethical issues because there are going to be people in the society who have access to the latest technologies, and there are people who are not having access to the new technologies. This is creating imbalances in the social system. This is a major ethical issue which is to be addressed. Another major area of interest is the nanotechnology. Nanotechnology, as you could see from this slide, is the convergence of a variety of technologies. Surface science, which talks about the various phases, the solid liquid phase, the liquid vapor phase, and the liquid gas phase, the aspects of properties at the boundary conditions defined by the phases. We have aspects of new mechanisms of electric storage, which is now possible. The only energy storage mechanism which was possible so far was the pump storage systems which are used in hydroelectric. But now we are having a variety of new battery technologies making it possible energy storage. New sort of capacitor systems or capacitor banks are also coming up, which makes electric storage feasible. Microfabrication, fabrication of miniaturized structures, and ICs at scale much smaller than which is at the range of nanometer, is the microfabrication that we are talking about. Molecular engineering, better materials and systems for specialized functions based on molecular properties. Semiconductor physics, the physics of devices, and application, amplification, and energy conversion. Molecular biology, biomolecules in various systems of cells, including DNA, protein, biosynthesis, etc. Organic chemistry, organic components and materials. So the entire gamut of a variety of sciences and engineering are called nanotechnology, where one dimension is sized in the range of 1 to 100 nanometers. This has made possible a number of applications. For instance, we have a very interesting aspect of corrosion resistance, which is possible in diesel engines. We all know that the diesel engines produce sulfuric acid and formic acid as combustion products. It has been demonstrated that nano zirconia powder can be used to coat the engine components by plasma spray. And the nano coatings create a lattice effect and keeps the corrosion away. So by using zirconia, which is a ceramic material, it is possible to use nanotechnology. Similarly, ultralight materials of alumina fibers of zeolite used as filtration members. Zeolites are aluminosilicates of sodium, potassium, silicon, calcium, barium, etc. Using such filtration members, it is possible to filter out bacteria less than 30 nanometer to achieve water purity of the levels of 99.999997. It's a huge application in terms of water processing. Ultralight materials could also result in energy, fuel, and material savings. We would see how ultralight materials are going to transform the renewable energy sector. I talked about removal of pollutants in diesel engines. There is another application again in the area of pollution. Earlier I talked about corrosion. Diesel oxidant catalysts using nanoscale platinum and palladium can reduce pollutant emission of vehicles, meeting stricter exhaust standards. Better photovoltaic cells, which are lighter and stronger, are available, and a variety of materials which can be used in defense, automobile, and aerospace are fast coming up. Let us now look quickly at the solar photovoltaic option. As you see, this is a flexible nanotechnology-based solar photovoltaic cell. The advantage of this is that normal VLSI technologies require high temperature process, but here it is only necessary to have low temperature process similar to printing instead of high temperature vacuum deposits. Therefore, with crystalline semiconductor, it is possible to the traditional process using crystalline semiconductor uses the vacuum deposits, whereas the new technology using gallium arsenide, cadmium telluride, copper, etc., it is possible to print on flexible polymerous material, and this flexible rolls instead of the rigid crystalline panels reduces the installation cost also. Now, one of the limitations of this is that the efficiency had been low, but using nanotechnology, it has been possible using excited electron interaction with holes and having a feature called carrier multiplication. It is possible to improve the multiplication of excitrons and thereby having a higher efficiency. Efficiencies increase as high as 65%, whereas in the flat panel crystalline semiconductor, usually the efficiencies are at the level of 25%. So using the electron multiplication technology, it has been possible to address the issue of efficiency. The cost of the solar material is also coming down very drastically with the application of nanotechnology. The advantage of the nanotechnology is that you can manipulate properties of materials very drastically. We know that a ceramic plate shatters when it falls because it is strong but not tough. A rubber ball has a different property. It doesn't break when it is dropped because it is tough, but it is squashed out of shape, which is because it is strong. It is possible to have the toughness and strength which are mutually exclusive in the normal materials, structural materials. It is possible to combine these features in the nanotechnology, which is making it possible to have a variety of new materials for structural applications. Acrylic-related synthetic material with thin nanofibers, it can be made stronger and tougher. This has made it possible to have lightweight armor, bulletproof vests, which has already been tried out in combat areas by the military. Now, nanotubes can also transform fuel cell technologies. As you are aware, the fuel cells basically use combination of hydrogen and oxygen to create energy. So it is the proton exchange which happens at the membrane which is critical. Using nanomaterials catalysts, it is possible to have fuel cells with much better properties, and carbon nanotubes can also be a very important component in fuel cells, transforming the possibilities of energy generation from various areas through the use of fuel cells, and this could open up huge possibilities in renewable energy as well. Now let us quickly go to the area of renewables. The whole focus on renewable energy had been basically because of the downturn in the oil market and the Paris Agreement. These are forcing. ഞാനൊരു വെബിനാറിലാണ് ഞാൻ തിരിച്ചു വിളിക്കാം. കുറച്ചൊരു കഴിഞ്ഞിട്ട് ഞാനിപ്പോൾ ഒരു വെബിനാറിലെ ലെക്ചർ സെഷൻ നടന്നുകൊണ്ടിരിക്കുക. വെബിനാർ ആയിരുന്നെങ്കിൽ എനിക്ക് പുറത്തേക്ക് വരായിരുന്നു. ലെക്ചർ സെഷൻ ഒക്കെ. There has been downturn of the oil market, and the tone set by the Paris Agreement is fast creating alternate paths for the future. The Paris Agreement was, as you are all aware, the COP21, the 21st Conference of Parties at the United Nations, creating a framework convention for climate change, was signed in 2016. This has declared that there would be we would try to achieve a carbon constrained scenario, which has access to decarbonized electricity in the developing world, which will emphasize on renewables and energy efficiency, and which will also look at widespread use of electric vehicles on the one hand, and also use of energy storage, minimizing the environmental impact of their behavior in industry as well as public use. Wind energy and solar energy rates have been coming down extremely drastically, and these also have contributed to the major breakthroughs in renewable energy. Now let us look at quickly about why we are talking about electric vehicles as a very important option here. The important reason is that 79% of the oil demand is from transport and the petrochemical sectors. This is the reason why there has been a unique focus on electric vehicles. The electric vehicle share of the fleet during 2015 to 2035 is shown in the figure. This is going to drastically change across the globe, and EV has becoming a focus. KDISC is involved in a collaboration with the Center for Development of Advanced Computing, Trivandrum, the power electronics team there, with Titanium, and also with the Trust Park of the Engineering College, Trivandrum, along with Vikram Sarabhai Space Center. We are trying to come up with the new lithium titanate batteries using the protection technologies available in titanium, and manufacture batteries for electric vehicles. As you are all aware, electric autos have come up as a part of the electric policy, which has been triggered by KDISC, the EV policy, during the last few years. And as part of that, we have been able to come up with electric autos. A number of buses for KSRTC have become electric buses. We have a chain of EV charging stations across along the national highway, the whole of the national highway from Trivandrum to the north. We have electric charging stations which are provided. We are now working on better battery management systems and also on improved charging systems jointly with CDAT, VSSC, and Titanium. So if your departments are interested in working on EV, another important area of EV is brushless DC motors. A number of magnetic materials which are available in our mineral sands is a huge opportunity for us to make breakthroughs in drives, EV vehicle drives, and other systems. And we are trying to see whether the KEL and other manufacturing facilities around would be in a position to come up using the breakthroughs in auto drives, which is being spearheaded by the Trust Park of the Government Engineering College, Trivandrum. The solar cost will fall down by 60% during the period 2015 to 2025, and by another 20% by 2035. Wind costs will come down by 50% during 2015-2035, and energy storage costs will come down by 80% during 2015 to 2035. This is going to drastically transform the renewable energy sector throughout the world. Now, another important breakthrough is quantum computing. I have shared with Vishal a YouTube video, which I would request Vishal to play. Vishal?
Yes, yes, sir, I will.
So good morning, Maker Fair. Thank you for coming early and kicking it off with Beginner's Guide to Quantum Computing. I'm Talia Gershon. I'm a research scientist at IBM at the New York office. And I'm actually a beginner myself. I just started learning about this 6 months ago. So I'm here to tell you that anyone can get started learning about quantum computing. And hopefully after learning a little bit about it this morning, you'll be motivated to learn a little bit more. So I want to start with 2 facts, right? Fact number 1, classical computers have enabled amazing things. The internet, they're part of how I got here. I was able to fly across the country on a plane, right? The electronic giraffe outside, blaring music, right? Classical computers have enabled just amazing things. But one of the things we don't often talk about is all the things they can't do, right? We talk about all the stuff they can do. There's so many things they can't. So I want to start with 2 examples of things classical computers are really bad at. And maybe they can solve small versions of these types of problems, but by the time the problem gets big enough to be interesting, we just run out of computing horsepower. So the first example is optimization, right? Optimization is, I want to find the best solution to a problem among many possible solutions, right? So here's a picture of a table. This is the table at my wedding. It's one of many tables, but you can see 10 people around a table. You have 10 people over for dinner. How many different ways are there to configure 10 people around a table? Right? The answer is 10 factorial, right? The number 10 seems so small, but 10 factorial is 3.6 million. There's 3.6 million ways to arrange 10 people for dinner, right? Next time you guys have dinner with 10 friends, share that fun fact with them, right? So when we go and do this, we consider some of the options, we make approximations, right? Because it's the only way we're really gonna end up seating people at all, right? But, the truth of the matter is, every time I add 1 person to my dinner table, the number of possible configurations grows exponentially, right? So we can solve small versions of this problem on classical machines, but we don't solve big versions of this problem very well at all. Second example is chemistry. This is a picture of a nitrogenase enzyme. Anyone who's ever eaten food should care about this enzyme. It's an important catalyst for the creation of ammonia, which is an important component of food, fertilizer, pharmaceuticals, and many other things. So this is the enzyme. I've called out 3 molecules iron sulfide clusters in this enzyme of different sizes. The one on the left is 4 iron atoms and 4 sulfur atoms. Believe it or not, this is the biggest of those iron sulfide clusters we can simulate on the biggest supercomputer that we have, right? It's so small. Why is that the biggest molecule of these 3 that we can actually simulate on a classical machine? And the reason is because to actually simulate what's going on in that molecule, I have to account for every electron-electron repulsion and every attraction of the electron to the nuclei. And that number grows exponentially the bigger the molecule, right? Every single electron exerts an electrostatic force on every single other electron, right? So when I add another one, I got to recalculate all the electron energies, right? So these 2 bigger clusters, they look so small, we can't simulate them. Okay, so there's actually many problems that have this characteristic. And what they have in common is this idea of exponential scaling. So there's a classic fable about the power of an exponential. And the fable goes, the creator of the game of chess brought the chessboard to the emperor, and the emperor said, I love this game. What can I give you as a reward? Right? And the craftsman said, okay, there's 64 squares on the chessboard. On day 1, give me 1 grain of rice. And every day after that, double the number of grains of rice I get, right? So on the first day, the emperor gives him 1 grain of rice. The next day, 2. The next day, 4. The next day, 8. And after a week, he had a teaspoonful of rice. But after a month, he had the rice production of a small country. And after the full 64 squares, it was Mount Everest of rice, right? So it grows really fast. The number 64 doesn't sound that big, but 2 to the 64 is an enormous number. So why do we think quantum computing is actually going to allow us to solve some of these problems we can't solve classically, right? So it boils down to 2 fundamentally quantum effects. One of the effects is superposition. So classical information is basically a string of zeros and ones. Everything that classical computing has enabled is, boiled down to a sequence of zeros and ones. So quantum computing or quantum information has this property that the states can exist in a superposition of 0 and 1, right? So not just 0, not just 1, but a superposition of 0 and 1, right? And you can also have complex superpositions of 0 and 1. So you start to be able to explore a much richer set of states. So if 1 qubit can be in a superposition of 2 states, then 2 qubits can be in a superposition of 4 states, and 3 qubits can be in a superposition of 8 states. So the possibility space you can explore is much more interesting and complex in quantum information. So the diagram on the right is showing you a superposition of 5 qubits, right? So you can be in a superposition of 32 states. So superposition is the first thing. The second thing is entanglement. This idea of entanglement is, okay, I've got 2 qubits and I'm entangling them together. So measuring the first qubit can tell me something about what will happen when I measure the second qubit. Okay, so entanglement is the second property that gives quantum information a really unique difference. So together, this allows us to totally change how we run algorithms, right? So take the optimization case. If I'm going to consider 3.6 million possible ways of configuring 10 people at a table, classically I have to consider each one individually, and then I have to compare them all, right? Here's how quantum computing is going to solve that problem. You take your qubits, you go into a superposition of all the possible states, all the possible configurations, and then when you encode the problem into your quantum computer, you're applying a phase on each of the states. The phase is, that kind of axis towards the center of that sphere you saw in the previous chart. You encode a phase on each of the states. And when waves are in phase, the amplitudes add. And when waves are out of phase, they cancel, right? So when you have noise-canceling headphones, what you're doing is you're creating noise that's exactly out of phase with the noise you're trying to cancel, right? So in quantum computing, you're going to go into a superposition of all these states. When you encode the problem onto the machine, you're applying a phase on each of the states. And then you're using interference. And you amplify some answers and you cancel other answers. Eventually you arrive at the solution. So it's just totally different, right? You just got to completely rethink how we're going to solve these problems, and that's kind of how quantum's going to do it. So it's obvious why the number of qubits matter, right? If I have 1 qubit, I can be in 2 states, and the more qubits I can have, I can be in a superposition of 2 to the n states. But another important factor is this error rate, right? I have to be able to control what's going on in the qubits. If I have really high errors and all of my operations don't work out as I expect them to, then that's not going to really work. So we're promoting a new metric called quantum volume, where we're saying, okay, if you increase the number of qubits, you can get to higher computational power, but not if you have really high error rates. So we have to both move towards lower error rates and higher qubit count, okay? So how do you actually build a quantum computer, right? This is how it should work theoretically. How do you actually go and do this in real life? So first of all, you have to have qubits that work in such a way that you can harness quantum mechanics. So we build basically artificial atoms. You know, atoms behave quantum mechanically. We build an artificial atom, and we make it out of a superconducting Josephson junction coupled to a microwave resonator. Okay, so this is what it actually looks like on the chip. You have these squares that are your qubits, and these squiggly lines are your microwave resonators, and inside of the qubit is a superconducting Josephson junction. And we got to cool this thing down to 0.015 Kelvin, where 0 is absolute 0, right? Room temperature is 300. This is significantly colder than outer space. And we talk to the qubits with microwaves. So this is what it actually looks like. This is how we talk to the qubits. We have inside of a dilution refrigerator, which you'll see on the next chart, we have all of these microwave cables that allow you to actually go and probe the qubits with microwaves, okay? And this is what it looks like in the actual lab. So these giant white cylinders, these are our dilution refrigerators. And here you can see my friend Nick working on one of the insides of the quantum computer. So great that we can actually do this, but did you know you can play with one for free today, anytime you want at our booth? When you go home, you can go and you can play with an actual quantum computer. We've hooked up a 5-qubit quantum computer in the lab, you know, through those microwave cables up out of the fridge, through the internet, available to you at this website for free. So you go to this website. When you do, you're going to find 3 different user guides. One is for total beginners. The beginner's guide is no math, just concepts. We're going to show you visualizations of how the qubits work. We're going to walk you through early examples. You know, what are the gates you can use? How do they work? How do you think about them? And then you go into the user guide. The user guide is going to show you some of the linear algebra you need to know. It's going to show you how algorithms work. We're going to give you a suggestion of 5 different algorithms you can run. We're going to show you what sequence of operations you need to actually implement that algorithm. And then when you're really interested, you're going to go into the developer guide. This is going to take you to our API online. It's a sequence of Jupyter notebooks that are written in Python. And you can actually send batch jobs to the quantum computer free. Just go and learn, right? We're putting it out there for you to learn. This is what it's going to look like when you click in to the Composer tab. On the previous chart, you know, there's 3 tabs. There's the Composer, the user guides, and the community. I'm going to talk about each of those. This is what it looks like when you click Composer. You're going to get to choose. Do you want to simulate it? You can choose to simulate, where you actually start with like 2 qubits instead of 5, because it's easier to get started learning.
Presentation.
Coherence time. Coherence time is how long does my quantum information last before it gets out of coherence. So for us, you know, we have 50 to 100 microseconds of coherence time, and that matters because it determines how many different operations can I do before I lose my quantum information. Okay, so now let's create superposition. We talked about superposition, let's create it. You drag and drop the different gates that you can perform. There are different logic operations that we show on the right. Just drag and drop it onto the graphical user interface. Here I've dragged the H gate, which is the Hadamard gate, onto the score, the line representing the first qubit, and I've done a measurement, and actually these are results I got this morning, having run 1,000 experiments on the actual quantum computer this morning. And you get roughly 50-50, 0 and 1, right? You're in a superposition of 0 and 1. When you measure, it randomly chooses.
Sir, you have started presenting. Sir, mute on, sir.
Sir, Unnikrishnan sir, mute ആണ് sir. Please unmute sir. Sir. Sir, sir, unmute ചെയ്യാൻ പറ്റും. Sir. Sir, mute ആണ് sir. Sir, mute ആണ്. Please unmute sir.
കേൾക്കാമോ?
Yeah, audible.
കേൾക്കാമല്ലോ. Okay.
Sir, ഇപ്പോൾ
Thank you.
കേൾക്കാം.
Now we would move to autonomous vehicles as the most important breakthrough area. I hope you can see the slide.
Yes,
The
sir.
various companies who are leading the autonomous driving patent race world over. We see Bosch, Audi, Continental, Ford, GM, Google. These are all the various companies who are leading the autonomous vehicle race world over. This would mean that they are trying to replace the car drivers with autonomous vehicles. Now the roadmap for the autonomous car is, we'll just see how the various counties in United States are faring on the roadmap for the autonomous car. As you can see, we have the blue color, which is the counties which have, this is a slightly dated slide. It was a few years back. We can actually update with the data which is available. The blue color shows the counties which have passed laws making legal autonomous vehicles. The orange color are the counties which are in the process of passing laws, considering passing laws, making autonomous vehicles legal on the road. This is going to drastically disrupt the conventional car industry. Now, the self-driving cars, in order to make them available throughout the world, the requirement is that the number of test miles with safe test miles should be 200 million is the sort of standard which has been proposed. Now, 275 million miles is the standard which has been proposed and accepted world over. Tesla has already crossed 130 million miles. This is the statistics in 2016. So this is drastically changing. A variety of companies, Tesla, Honda, Hyundai, etc., and Ford are in the lead for autonomous vehicles, for creating self-driving cars. The timeline for full automation, we see a variety of companies. Tesla, Nissan, Volvo, Daimler, Ford, Intel, and Google also. And interestingly, the Baidu, one of the leaders in that, is a company from China. All these companies are on the lead and working towards the possibility of looking at autonomous vehicles. Along with the autonomous vehicle, there had been a huge movement towards autonomous delivery drones, and COVID has made this much faster. Drone delivery was a fancy thing just before COVID. Defibrillators were distributed by students as a part of automobile drone technologies in Netherlands. Similar services were being done in Nordic countries. Domino's has partnered with in New Zealand to have the first commercial drone delivery services. Marriott International is using drones to deliver cocktails to tables of guests. In China, Beijing in 2017, a variety of delivery drones were used for delivering courier packets. Boeing unveiled a prototype of cargo drone which can carry up to 227 kilogram payload. Along with the drones which are available above the land, it is also possible to have underground autonomous underwater vehicles. This has been powered by using electric motors, direct drive thrusters, and also GPS and aquatic positioning. Extensive sensor, depth sensors, sonars, thermistors, etc. are being used for this technology, making ocean surveillance and military applications possible using underwater vehicles. So this is a breakthrough that we are seeing in terms of autonomous underwater vehicles. Slide movie and slide show mode slide show mode slide show mode Another major breakthrough which has been possible is in the area of microsensors. So we'll go quickly to microsensors, which is making drastic breakthroughs in soil and agriculture related activities. Two major technologies are impacting agriculture world over. Number one is infrared imaging for pests. And using the infrared imaging, it is possible to use drones widely for application of pesticides and insecticides. Soil analysis precisions are reaching much higher levels. By using, it is possible to use microsensors at the root zone of plants for achieving better levels of nitrogen, potassium, phosphorus, and along with that, micronutrients in the soil can be also managed by using precision sensor information. This has opened up a new area, what is called precision agriculture. So precision agriculture, drone agriculture, and multispectral techniques which can create signatures of jobs are drastically transforming agriculture. Now we are coming to manufacturing process. Manufacturing process have been also drastically changing. The familiar statue at the top of the screen is using what we call a subtractive process. And you would realize that the other manufacturing processes are using forming, molding, etc., which are all very familiar to you. But a new form of additive manufacturing process called 3D printing is coming up, which is drastically altering the manufacturing scenario. This is an MIT-based 3D printer which uses an inkjet 3D printing. A powder bed and the inkjet head is developed by MIT. The inkjet print head moves across a bed of powder, selectively depositing liquid binder material. A thin layer is applied on the completed section using computer-aided design techniques, and this makes it possible to have very precision 3D printing. Another mechanism of 3D printing is the fused deposition modeling, which uses a continuous filament of a thermoplastic material. This is fed through a large coil through a moving heated printer extruder head. The head is moved under computer control to define the printed shape. A third method of stereo print is stereolithography, which is similar to the very large scale integrated circuit manufacturing technique, which is basically optical deposition of polymers using photopolymerization, by which light causes chains of molecules to link, forming polymers. The polymers make up the body of a three-dimensional solid. Another method of 3D printing uses laser sintering. Use a laser as a power source to sinter powdered material, typically nylon or polyamide, synthetic polymer amide. Aiming the laser automatically at points in a space defined by a 3D model, binding the material together to create a solid structure. A variety of applications of 3D printing are coming up in aerospace for making engine, compartment, cabin accessories, air ducts, etc. Automotives, we have air ducts, full-scale panels, lights, cast materials, brackets and handles, which can be readily 3D printed. In medical area, we have surgical instruments such as forceps, scalpel handles, clamps, prosthetic limbs, liver and intestinal tissues created in vitro by using 3D printing. So 3D printing is very drastically altering the manufacturing scenario. I will show you quickly a short video on 4D printing from MIT. It doesn't have an audio, so you can hear it from my presentation itself. It's only music which shows. It is a 4D printer, which is a process by which a 3D printed object can transform into another object under the influence of external energy inputs such as light, temperature, or environmental stimuli. Here, the material is transforming because of very small pressure which is given on the body. So this is the 4D printing technology which is being developed by MIT, which makes it possible for us to have 3D printed devices transform itself in shape with an external stimulus. Now I'm going quickly to robotics, another area of breakthrough. You see as a part of the COVID situation, we had robots, lifting robots, seed growing robots. In the agriculture scenario, we see plant nursing robots called hortibots, lettuce bots for organic weed elimination and thinning of lettuce, robotic harvesters to produce fresh produce, agriculture robots for weed detection and spraying, and the robot milker for providing high quality milk, which is much more productive and efficient rather than compared to the existing milker machines. So wide applications of robots in manufacturing and agriculture are possible, and in service area also robots are coming up as major opportunities. We will quickly go into material science, advanced materials, new materials which have become possible. What I'm showing is graphene. The Digital University Trivandrum is trying to establish an international graphene facility as a part of a national grant from the Prime Minister's office. The negotiation has just been initiated. Graphene is about 200 times stronger than steel. It is 1,000,000 times thinner than human hair. It's an efficient conductor of heat and electricity. If it becomes price competitive, I mean, there is no need to say it could disrupt manufacturing and infrastructure industries drastically. Another interesting material is polyhexahydrotriazine. It is a thermosetting plastic. In aerospace, the polymer could be used in building of airplanes like wings, etc. The advantage is that if the body breaks, then it can be very easily regenerated and healed. Similarly, if I have a break on my TV screen, on my LCD screen, if I am using polyhexahydrotriazine, it is possible to heal that. So, because it is a polymer thermosetting plastic, the greatest advantage of the polymer thermosetting plastic is that it is also fully biodegradable, and therefore there is no danger of trash. The physical properties are malleable, strong, lightweight, flexible, and heat resistant. So the materials like polyhexahydrotriazine and graphene are no longer science fiction. This is going to be reality, and this is going to transform our manufacturing so drastically. So with 3D printing, robotics, and the advent of these new materials, we are going to see a huge revolution in manufacturing. Now coming to Internet of Things. We saw the internet revolution which connected the internet, the computers. Now the relationship between the computers in a network, it can be a relation with washing machines, it can be a relation between cars, it can be a relation between gadgets. My wristband, which I use for monitoring my sleep levels, my heart rate, and also my glucose level in the body, is connected to my children and my wife who are staying long at distant places. It is all possible because of the possibility of using Internet of Things, which is drastically transforming the service sector and the manufacturing sector. KDISC was involved in a project with Intel, where we have developed a technology for reducing the number of collisions in KSRTC vehicles, made possible because of the new technology of Internet of Things. Another area where we had been working along with a small startup from the Maker Village is in the transport of blood bags. The blood bag transmission between the General Hospital Trivandrum and the Parashala CHC. The blood bags are being transported in ordinary ice bags. The addition that we have brought in is that we have brought in an RFID and an IoT sensor which transmits continuously and manages the humidity level and the temperature level inside the ice bag. This has reduced the perishability of the blood bag in the transmission between the hub at General Hospital and the Parashala Community Health Center, which is a spoke. Now the health department has found this extremely advantageous and have decided to replicate this technology, which is developed by Bagmo, the startup, which is comparable to similar technologies available in the Americas and the Europe at the state level. So Internet of Things is going to be a hugely important technology, which is important for managing traffic control, which is important for managing vehicle and vessel movements, which is important for supply chain management. In another project which KDISC is heading, we are trying to create what is called a Kerala food platform. In Ernakulam district, we are working with a agriculture cooperative bank, Palliyakkal Agriculture Cooperative Bank, where we have created a QR code based traceability system for vegetables which are moving from the farmer. So it's a farm to fork innovation which we have tried out, where it is possible to say this particular brinjal or this lady finger has come from this farmer. And so the authenticity of the product as an organic product can be established. That doesn't use Internet of Things, but it uses a very simple technology called QR code. So it is possible to use such technologies and involve seriously in supply chain management and material movement, which is going to be extremely important. The maintenance need of driving of vehicles, forklifts, etc. can be continuously captured by using IoT and also food packages. I was just explaining the example of the Palliyakkal, which is basically modeled on what Walmart has got, a technology which says the apple has been picked up from this orchard at this time, and there is a chip inside the apple which captures the entire information on that. Just like we have an RFID chip on the textiles, on the ready-made shirts and other materials that we get from a, textile shop where we go to buy such ready-made articles. So Internet of Things is going to be a very major technology which is going to transform. Another important technology is the blockchain technology. Blockchain, as you are aware, is basically a decentralized cryptographic system which is helping the management of information systems in an entirely new manner. The ATM and money transfer systems in banks have been made possible, as you all know, through what is called the integrated banking systems, which are centralized bank systems. Drastically, such centralized banking systems are giving way for the new blockchainized, decentralized systems. The blockchainized, decentralized system, as I indicated, the example of Palliyakkal, are making feasible the traceability for food supply chains to prevent contamination. It is possible by using blockchains to have smart contracts across the supply chain segments between the various components of the segment, making supply chain transactions and record keeping more secure and transparent. This is going to drastically transform the fintech sector and the peer finance and peer lending systems world over very drastically. Accelerated Blockchain Competency Development Program by KDIST aims to put Kerala at the top of the blockchain hub by 2030. We are planning to create 20,000 blockchain engineers through the Kerala Blockchain Academy and ICT Academy. The blockchain technology training is being imparted in engineering colleges and polytechnics in a big way, making use of the advantage of the various technologies. We all know about the 5G technology, which is coming up very fast. The K-phone which we are laying is going to take 4G throughout Kerala. When I first started using the telephones, they were immediately after the traditional analog telephones. We switched over to the first generation digital telephones in 80s. They had a speed of 2.4 kbps. They were also analog systems. They had low phone size and voice quality was also much low and battery life were low. That was the transition from the traditional dialing type of telephones which we used to the first switch type telephone systems, which were still analog. They were called 1G. Subsequently, we came up with the second generation of telephone technologies, which used narrowband, which made possible SMS and MMS. That was when the pager technologies were becoming popular. The speed of the system was 50 kbps was the maximum speed that was possible. Subsequently, we had the 3G, which was in 1998, which made possible wider applications of mobile. That was when the internet was also made available on the mobile. And thanks to the 3G technology, it was possible to make video calls. The maximum speed was 2 Mbps for stationary devices and 384 kbps for moving vehicles. We now have 4G popularly in India, which supports the video conferencing. The Zoom and the web conferences became very popular because of the availability of 4G, which has a speed of 1 Gbps, and in moving vehicles 100 Mbps. The K-phone will reach out this Gbps bandwidth throughout Kerala and also to the 20 lakh poor households, providing universal internet for the first time in a state, of course, following Estonia and a few Nordic countries. We are on the transition to 5G. 5G is available in many countries now. From 2020 onwards, it is available. It has a speed of 20 Gbps. It has a very low latency of 10 milliseconds. It promises faster data rates, high connection density, and also, more importantly, energy savings. We will quickly go to the platform technologies. That's the last slide as far as Industry 4.0 technologies are concerned. And then we will go to a little bit on entrepreneurship, and I will close my presentation. I will quickly talk about the platforms, which is becoming a very important side. These are called multi-stakeholder platforms. The 2014 Nobel Prize in Economics was given to Jean Trolle for multi-sided platforms, which is basically the Uber. Uber is very familiar to everybody. If you have more drivers, then you have lower prices because of competition. If you have less drivers, if you have more passengers, then you have less idle time for drivers. So there is an interaction between both sides. There is the numbers on each side makes an impact on the other side. This is the most important feature of Uberization, which is made possible in multi-stakeholder platforms. The multi-stakeholder platforms have become possible because of huge transformation in microelectronics technology, more powerful chips, the speeds of internet and the World Wide Web, and the broadband communication possibilities made possible through 5G and the programming languages and operating systems, and also what is called the cloud technology. These are made the platforms. Now I am coming to entrepreneurship. Let us quickly look at how the Silicon Valley has become a Silicon Valley and Stanford entrepreneurship system have become established as the first model of innovation promotion and startup building. Nobody knows that the great revolution in Silicon Valley was possible through a huge government investment by the American defense establishment and industry. When the Sputnik 1 was launched, the American political leadership asked Ford, Lockheed, and IBM to move their facilities into the Silicon Valley. It was the initiative of these companies, these hardware companies, subsequently which resulted in creating the Fairchild and the Fairchildren, the Intel, the AMD, and NVIDIA, which became the hardware industry. And NASA bought back their products in 1960 It was this huge involvement of the industry and also the government, which established the innovation system in the Silicon Valley and also made use of the Stanford, MIT, and the Cambridge systems around. In number one, providing abundant capital, providing collaboration with the industry, providing government support for and promoting a risk-taking culture, and also bringing in talented, diverse, and imaginative students, and also a community of professors, scientists who were ready to give back. All these have created what we call the Silicon Valley and the Stanford entrepreneurship. It is not only a new innovative generation which was there, but also the huge government support and the support systems that were made it possible. There was an excellent academic system. The Stanford University with 2,000 faculty, 21 Nobel laureates. The Berkeley University of California, Berkeley, with 7 Nobel laureates. The Stanford Research Park, which transfers technology from the university to the industry. The alumni of Stanford, which created 7,054 companies and 5.4 million jobs. Similar models have been emulated by China, which is leading the technology revolution now. The huge internet giants in Shanghai have positioned BAT, Badu, Alibaba, Tencent are corporations which are becoming important in Beijing, Hangzhou, and also in Shenzhen and Shanghai. The university systems. The Fudan University having a ranking of 100 international. Chiao University having a ranking of 189. East China University of Science and Technology, which is in the top 1.5%. So all these universities and along with the internet giants are now leading the innovation in China. And the Chinese government had made a huge policy transformation of industry and universities working with enterprises, which made possible the huge transformation of the industry and the growth of startup and innovation in China. In Kerala also, KDISC is spearheading the innovation program, working together with ICT Academy, the Startup Mission, the Digital University, KSIDC. All these agencies are coming together for angel funding. Promotional activities in data sciences, accelerated blockchain technology, and a variety of industry 4.0 technologies have been initiated. Innovation promotion programs called the Young Innovation Program for youngsters in colleges and schools have been initiated by KDISC. Similar innovation programs for MSME promotion, one district, one idea. Innovation promotion programs, one local government, one idea, local innovation, all are being driven by KDISC as a part of this program. A variety of coordinated projects in agri-tech, in fintech, in MSME, in geriatric care are being triggered by KDISC as a part of the knowledge mission. I look forward to the professionals who are assembled for this session in the various engineering colleges and other technical institutions to work together with KDISC in taking this innovation race seriously and taking this initiatives for the knowledge mission, establishing a knowledge society in Kerala, a reality, and make your own contribution to that. I would close my presentation at this level. I have run you through all the facets of the Internet 4.0 and the various aspects of entrepreneurship development world over, starting with the Silicon Valley, China, and what is happening in India and Kerala. Thank you.
This session has come to an end.
Right.
If you have any queries, please discuss with sir.
Sir, sir, I have a question, sir. Actually,
Please.
70 colleges are participating in this program, sir. So, how can the faculty members and the colleges can interact with kids?
Please, ma'am. Hello.
Hello, sir. Vishal,
Please.
am I audible?
Yes,
Am
yes,
I
please.
audible?
Yeah, please, ma'am.
Sir, actually, more than 40 to 60 colleges are participating in this program. So almost all the colleges are under KTU, and all the programs running under KTU. And how the colleges can associate with the KDISC, sir?
Yeah. Number one, as a part of the Young Innovation Program, we have just initiated the institutional registration. Each institution can come up with 3 facilitators as a part of the program and a student ambassador. And there is also a provision for a retired facilitator, or retired of the college professor being also part of the facilitation team. We are creating a 5-member facilitation team in each institution. So the faculty members can easily connect with the Young Innovators Program. And whoever connects with the Young Innovation Program will be connected as a part of the Innovation Network. We will be providing regular training programs and support systems for the faculty members as well, trying to bring them and help them in the innovation journey, trying to help them guide the students in a better manner. We have already created a mentor-mentee platform for this. We are doing regular trainings on design thinking, basically based on the Stanford methodology. We are now creating a new mentoring framework with the help of IIM Calicut by using what is called a new product development technology for the fussy front end, essentially where fussy ideas are coming in, they can be improved by using the industrial engineering based methods of new product development. So we are creating an ecosystem of teachers and students throughout Kerala. Whoever is interested in innovation, they can connect to the Young Innovator Program network as a part of this institutional registration and the facilitator registration. Shortly, we are also announcing an innovation fellowship for staff members, which would be an additional payment to the faculty members who opt for becoming the innovation fellows. They would be given a supporting honorarium, which would be provided for providing professional support to the mentees on a commitment basis. That's also coming up. So these are all avenues where the faculty members can associate with KDISC as a part of the Young Innovation Program and other innovation programs. Thank you, madam.
Thank you so much, sir. Thank you so much. Vishal, any other queries from participants? Vishal, sir? Vishal, sir?
Hello.
Yeah, please.
Yes.
If there are any queries further, participants can ask. Otherwise, we will wind up this session.
Nidin, before that, Unnikrishnan sir, that was indeed, but a detailed and informative ride through various aspects of Industry 4.0. Actually, thank you so much, sir, for accepting our invitation and sharing your valuable ideas. Thank you so much, sir, on behalf of the department and college. Thank you. And on behalf of all the participants, thank you very much, sir. And I invite officially giving the vote of thanks from Nitin. Professor Nitin. Nitin, sir?
Hello. Sir, we are expressing our sincere gratitude for your presence and blessing this function with your session. And I also appreciate your contribution towards supporting facilitators of learning as well as engineering aspirants around Kerala. On behalf of our mechanical department fraternity, I express our sincere gratitude from bottom of our heart to Dr. P.V. Unnikrishnan from KDISC. I hereby express our sincere gratitude towards you. Thank you, sir. Thank you very much.
Thank you.